Every second, petabytes of data traverse the globe, moving as light pulses through a massive, interconnected physical architecture. This diagram shows the top tier of that physical hierarchy. At the center is an extremely high-speed backbone, which pushes massive amounts of data out to regional distribution hubs known as Network Access Providers, or NAPs. Below the NAPs, this diagram illustrates how the network steps down into local internet service providers, branching out further through local lines until it reaches the modems of individual end users. Across this hierarchy, the physical equipment is wildly diverse. An enterprise server farm operates on entirely different hardware than a consumer laptop or a local cell switch. Running a raw copper or fiber wire between two of these varying devices guarantees absolutely nothing. Without shared operating logic, they cannot exchange information. The immense geographic reach of these cables requires a strict, universally adapted set of rules to translate data across those incompatible hardware environments. Consider a single local area network. Its proprietary hardware dictates specific physical parameters. Network A might transmit data in 128-byte packets using a positive 5-volt signal. A completely separate Network B might use 256-byte packets and a negative 5-volt signal. If you run a physical wire directly between them, the communication collides and fails. The voltage is wrong and the packet boundaries do not align. To fix this, an intermediary hardware device called a router is placed between them. A router contains multiple network interface cards, allowing it to physically plug into and absorb the differing signals of incompatible networks. However, the physical media access control, or MAC addresses, hard-coded into those network interface cards, only function within their own specific local network. They have no concept of the network on the other side of the router. The hardware cannot solve this problem on its own. It requires the TCP/IP protocol suite, a universal software abstraction layer that forces these proprietary systems to agree on a common language. The Internet is not the physical wiring. It is the agreed-upon set of logical protocols bridging those isolated islands of hardware. Managing routing, hardware translation, addressing, and error correction simultaneously is extremely complex. Writing a single massive piece of software to handle all of it at once creates an inflexible system that breaks easily when hardware is upgraded. This chart shows how engineers solved that by dividing the tasks. Unlike the theoretical 7-layer OSI model, TCP/IP uses a modular 4-layer hierarchy. The top two, the application and transport layers, handle high-level software processes. This section of the chart illustrates the lower half, the network or internet layer, which handles global routing logic, and beneath it, the interface layer, which interacts directly with the physical network. The interface layer has one isolated job. It takes standardized data packets from above and encapsulates them into the specific frame formats and electrical pulses required by local hardware, like an Ethernet or token ring connection. By hiding the messy, hardware-specific translation inside this bottom layer, the upper application layers never have to know if a computer communicates via copper wire, fiber optics, or microwave relay. This strict layer isolation guarantees forward compatibility. Physical hardware can rapidly evolve over decades without forcing developers to rewrite the core software of the network. Moving up one step brings us to the internet layer. Its primary purpose is to assign a single hardware-agnostic identifier to every device on the network. It achieves this using the Internet Protocol address. In IPv4, this is a 32-bit logical address, written as 4 bytes and stored in a big endian format, meaning the most significant byte is read first. This chart shows the 32-bit address structure, split into a network ID and host ID. Binary prefixes dictate the class. Class A allows massive networks, while Class C restricts to 256 hosts. The bottom rows show Class D for multicasting and E for experiments. Administrators can further slice a primary network ID by applying a subnet mask. This applies a bitwise logic operation that mathematically divides a large block of IP addresses into highly specific, localized subnetworks. These logical IP addresses project a unified, highly structured mathematical map over the chaotic physical geography of global hardware. But a major translation problem remains. Global routers operate strictly on these logical IP addresses. The final local delivery of the data, however, requires the hard-coded physical MAC address of the destination computer.
The Internet layer bridges this gap using the Address Resolution Protocol, or ARP. When a router knows the logical IP address but lacks the physical hardware destination, ARP broadcasts a query across the entire local area network. It pings every connected device until the exact machine responds with its unique MAC address, allowing final delivery. The protocol also accounts for internal diagnostics. A designated loopback address, usually 127.0.0.1, allows software applications to communicate with one another on the exact same machine without a single packet ever touching the physical network hardware. ARP provides the essential tether. It links the vast abstract map of the logical internet directly down to the physical metal of individual machines. To physically transport data across that logical map, the Internet Protocol defines an independent, connectionless vehicle known as the datagram. Every datagram carries a 32-bit wide header. Before transporting any user data, this header carries complex metadata required to navigate independently. One crucial piece is the time-to-live field. Every time the datagram jumps to a new router, this number decrements by 1. If a packet gets caught in an infinite routing loop, bouncing endlessly between routers, the time-to-live field eventually hits 0. This triggers a forced kill switch, immediately destroying the packet to prevent catastrophic network congestion. Another key field is the 13-bit fragmentation offset. If a large datagram hits a physical network that can only handle smaller packet sizes, the router splits the payload into multiple smaller blocks, each assigned a new offset number. This pointer guarantees that even if a large payload is broken down to navigate through rigid hardware limitations, it can be perfectly reassembled in the correct order at its final destination. The payload is meaningless if it cannot reach its target. This specific metadata ensures a packet can survive an unpredictable, multi-hop physical route. Inside that same header is an 8-bit protocol field, which dictates what happens the moment the datagram arrives. Because IP is only concerned with host-to-host delivery, the protocol field explicitly identifies which higher-level software process in the transport layer must receive the data next. The Internet Protocol is strictly a best-effort delivery system. It moves packets independently, providing zero guarantee that the data will arrive intact or in sequence. To solve this unreliability, data is handed to the Transmission Control Protocol, or TCP. It takes the scrambled datagrams delivered by IP, forces them into strict chronological sequence, performs error checks, and calls back for missing pieces before allowing data to pass. This rigid reliability requires processing overhead. For processes where delay is intolerable, like streaming audio or video, engineers instead use the User Datagram Protocol, or UDP. UDP prioritizes speed over connection checks, accepting dropped packets to maintain a continuous feed. The flexible, autonomous routing of the IP datagram ensures data can navigate any physical hardware path. When paired with the strict, reliable stream assembly of TCP, the protocol suite resolves the hardware incompatibility problem, creating a robust, unified global network.